Hello, welcome to Physics 2 Lab 4 Circuits by me, Pratha Mingale. Introduction, the goals of this lab, we have three main goals. The first is to use energy and current conservation laws to predict the behavior of circuits. The second is to use multimeters to measure values of current and potential difference at different points and across different components. And the third is to observe the functionality of a capacitor and how it charges and discharges. Some quick results. We prove the loop rule to be true, where the sum of the voltage difference equals 0 around a loop. And the slope of our RC circuit was negative 0.0298, which is close to the predicted value of negative 0.0196. Some physics fundamental formulas that we use here. Ohm's law, we all know, V equals IR, how to find these values. Kirchhoff's junction law, which states that the current going into a junction has to equal the current going out of the junction. And Kirchhoff's loop law, which states that the sum of the potential differences around a loop equals 0. So experiment 1. The system, before that, there's a quick diagram of it here. These resistance values are incorrect. Our resistance values were different than these. They were 12 and 51, but this is straight from the lab report. The system is the batteries, the wires, the multimeters, and the resistors. The surroundings is the table, the rest of the room, and the general earth. And the initial conditions is that with an open circuit, the current readings in the ammeter start at 0 amperes. The setup you can see here, current 1 equals current 2 equals 0.0206, which matches our predictions that the current is the same at both ammeters. For some observations and some tests we did, the backwards ammeter reads the negative of this. And if you replace an ammeter with a voltmeter, it leads to a voltmeter reading of negative 3 volts and an ammeter of 0 amperes. And this is because the voltmeter has a really high resistance, and the current would become 0, and the voltage is really high across a voltmeter, or the potential difference, so that the sum of the potential differences equals 0, like the law. Some results, once again, these resistance values are different. The readings we got here show that the loop rule is true. It matches our prediction. The sum of the potential differences across the components sum up to 0. And you can see here, this drops by 1 volt around, and then this drops by 2 volts, leading it to 0. And attaching a voltmeter to measure the potential difference doesn't affect current because the voltmeter has a very high resistance, so the current doesn't take that path. So experiment 2 you see here, except without a switch, we just manually connect the wires. We have a battery. In the system, we have the batteries, the wires, the capacitor, the light bulb. The surroundings is everything else. And initial condition is open circuit, current is 0 amperes, capacitor has 0 charge. So setup and observations. They're over here, but I'll highlight these first two because those are the important ones. When the circuit is connected to the battery, the light is bright at first and slowly dims with time as the capacitor gets charged. And when the light is just connected to the capacitor, it is again bright at first and dims with time as the capacitor gets discharged. These are about currents and the direction they flow, which is pretty self-explanatory. So some results here. We have just information. The capacitance of our capacitor was 1 farad. It was a massive capacitor. And the light bulbs. These are the two light bulbs we used and their associated resistances. And here's the time to charge and the time to discharge them. We then did our recording with the 51 ohm light bulb. And you can see here, these were its, as time progressed, this is how the potential difference of the capacitor decreased. So I converted that column of potential difference to ln potential difference and plotted it versus time to get this graph. And we know from the equations that the slope of this graph is equal to negative t over rc. So I went through and calculated, this is the theoretical value of our slope, this is the actual value of our slope, which is fairly close to each other. We'll go over some reasons for why it might not be correct here. So some assumptions: the batteries are fully charged at 1.5 volts. The multimeters can accurately measure their readings. The resistance values written on the light bulbs are correct, and the resistance in the wires is negligible. These are 4 assumptions. Some errors could be human error in transferring the data from the multimeter to the spreadsheets. And the second, and this is what I think is the main point of error, is that there's not enough data points. We've only have about 10 data points here, and for a more accurate reading, we should do it over a longer period of time. What if question number 1? Ignore the first part since it was done real. The virtual ammeter behaves differently because it actually has 0 resistance rather than our ammeter, which has a very small resistance. This leads to more accurate readings of current and makes the loop rule more precisely true. What if number 2? Once again, this is irrelevant for us. We look at the second half. Since we did it with real, So the capacitor doesn't charge instantly like we predicted because there is some internal resistance associated with both the battery and the capacitor, which leads to an equivalent resistor, it basically leads to an equivalent resistor in the circuit. Thank you. That was my lab.